Thank you.
Thank you very much. Good morning, everyone. Well, actually, I was in Luxembourg and I will be in École Polytechnique near Paris. There is not an École Polytechnique in Luxembourg yet. So first of all, I'd like to thank the organizers for inviting me. It's really a pleasure to be here. I will be talking about large deviations and dynamical phase transitions in finite size open exclusion processes. And I will be, just like Rosemary yesterday, I will be taking the physicist approach, which is to compute things and assume that everything works fine. I think there are many connections between what I'll be telling about and what, for instance, Stefano said last week about the infinite volume case. I'm not an expert on the infinite size case, so if you do see connections, or if you hear me say things that are either trivial or stupid, do let me know. And of course, never hesitate to interrupt to ask questions. So I will start by very broadly introducing context and some notations on large deviations. I will then be talking about the standard asymmetric simple exclusion process, which is integrable. I will give the definition quickly and then a brief overview of known results about the dynamical phase transition that I'm interested in. Then I will generalize that exclusion process by adding site-dependent jump rates and local interactions between the particles. And I will show what can still be done analytically in that case. And then I will conclude. So very, very generally speaking, the central question in statistical physics is how to go from microscopic dynamics to macroscopic behavior of that model when rescaled in some appropriate way. So the most simple case is to just consider a random walk on a lattice. And as you know, if you zoom out and rescale things appropriately, what you see is a Brownian motion. So more precisely, if I have jump rates that depend on the direction, for instance, and possibly on the site, microscopically, this thing evolves according to a master equation, which contains the jump rates for every direction. And at the large scale, if those rates are not symmetric, the particle will move according to this equation where I forgot a square root around the d here, which comes from the possible asymmetry between those rates. And then around that constant drift, the particle fluctuates with a certain amplitude d, which multiplies a Gaussian white noise, and now there should be a square root. This is, okay, the really simplest case. Now, what happens if you take n, a large number n of those particles, and they are independent? Well, and you want to look at the behavior of the density particles at the macroscopic scale. At the microscopic scale, the master equation for the system looks formally a bit more complicated. You have transitions between configurations of particles that are one jump away from each other. The rates here are actually a very simple combination of the individual jump rates and the number of particles at the site of the jump. And at the macroscopic scale, the density evolves according to a continuity equation with a current here, which contains three terms. There's a constant drift part, which comes from the force applied to every particle. There's a self-diffusion term with a diffusion matrix D, which comes from the diffusion of every particle. And there's a new noise with an amplitude d rho over n, which comes from the uncertainty that we have because the number of particles is large but not infinite. This equation is, well, the deterministic part of this equation is qualified as hydrodynamic by analogy to the equations of fluid dynamics. And this is very interesting thing is what happens, the interesting question, what happens when you add interactions between the particles? At the microscopic level, what happens is fairly straightforward. The rates become more complicated. In some way, if you add simple interactions, they won't get that much more complicated, but the shape of these things doesn't change that much. But at the macroscopic scale, one of two could happen: either that hydrodynamic behavior is maintained, but the terms in that equation become more complicated, possibly nonlinear, or that structure is completely lost. For a system close to equilibrium, the macroscopic fluctuation theory tells us exactly that this structure is maintained with more complicated dynamic coefficients. I will be looking at systems which are very far from equilibriums. The asymmetric simple exclusion process has a force term which scales with the size of the system, which can be understood as a diffusion term which scales inversely with the size of the system. And in that case, in principle, nothing is known, but we will see that some things do look nice anyway. To introduce some notations, well, you probably all know exactly what large deviation function is, much better than I do, but let's just to introduce notations. The most simple example, you take n coin flips with a certain probability for heads, and if you're interested in the probability of the ratio of heads, as you know, the law of large numbers tells you that this number converges almost surely to the probability of heads p, and the central limit theorem is a bit more precise. It tells you the way that it converges in absolute is through a Gaussian distribution with a variance 1 over square root of n. This is very good approximation for R around P, for R close to P up to 1 over square root of n. It's a terrible approximation for R outside of one variance around the mean. And a much better approximation is obtained by large deviation function, which you get by taking the rescared logarithm of that probability, just like you would do for free energies. Well, it is, in this case, a free energy. I'll be looking at continuous time Markov processes and dynamical large deviations of those. So here's an arbitrary continuous time Markov process with 3 states and some rates. I could look at the probability of staying for a certain fraction of time in a certain state, which would behave with a large deviation, a certain large deviation function. I will be interested instead in the probability of observing a certain number of jumps from one state to another with a certain rate in time, which I call here J, which is the flux between A and B. And this also follows the large deviation principle with some other large deviation function. In practice, the way that I will access those large deviation functions is by taking the rate that I want to monitor, the jump that I want to monitor, and adding counting field to that rate, only to the non-diagonal part of the rate matrix, so that every time I use this thing, and I can generate moments of current that I'm looking at using this. And it's a very famous result that if you look at the largest eigenvalue of that biased Markov matrix, which is, it has a largest eigenvalue which is non-zero, then that largest eigenvalue is the generating function of cumulus of the observable that I'm looking at, and it's related to the large deviation function of that same thing through a Legendre transform. Here I'm talking about discrete spaces with finite states, a finite number of states, so there's no concavity issue. The Legendre transform will always be valid. Right, so the specific model that I'll be looking at is the totally asymmetric simple exclusion process. It's a very, very simple, elegant model where particles jump from site to site towards the right with a rate that I set to 1 just to fix the time scale. And then particles can enter the system at the left with rate P0 and exit at the right with rate PL. And in the bulk of the system, jump on a site which is already occupied. This is a very simply defined model, but has very, very deep physical behavior. It's rightly considered as the Ising model of non-equilibrium statistical physics. Also a very reasonable model for some actual physical or biophysical models. It was devised to model the motion of ribosomes on RNA and is still used for that and for molecular motors. It was devised by mathematicians at the same time to look at non-intersecting random walks. It's related to a lot of different physical, interesting physical systems, so it's also studied for those reasons. And last but not least, it happens to be exactly solvable. That is a blessing and a curse. This means that on that model there are very elaborate analytical techniques that allows you to get very precise, exact results. It also means that a large part of those techniques are not transposable to any model. But we will see that there is still hope. As I said, I will be looking at the current of particles in that system. Since it's dimensional and I'm looking at stationary fluctuations, bond that I choose, I could just take the average of the, and in fact this is what I will do because it makes calculations simpler, but it doesn't matter. The way that I will get to the large deviation function of that current, as I said before, is to look at the bias to estimate, take a Legendre transform. So very quickly, a few not so recent results about large deviations in that standard exclusion process. So from exact calculations, for a large size current close to its average, so this is moderate deviations in the sense that it's not at the Gaussian scale, but it's not for a finite deviation of the current either. It's for J close to its average. Everything depends on the boundary rates, but the most interesting case is when you take the two boundary rates larger than 1/2, in which case the average current is 1/4. And what we find is that for fluctuations smaller than the average, the large deviation function scales with a certain power law. This is compatible with, so this expression can also be obtained by taking the macroscopic fluctuation theory joint rate function, taking a very large drift, but under the proper rescaling becomes a very small diffusion, and then extremizing the rate function on the densities to find the current. So this, using the macroscopic fluctuation theory for the totally asymmetric exclusion process was first proposed by Boudin and Derrida in 2008. These exact results confirm that it's a good idea. It works. Now, when we look at fluctuations larger than the average current, we get a different power, which is nice. We have a phase transition. More importantly, large deviation function now scales linearly with the size of the system, when before it didn't depend on the size of the system. This scaling with L is not incompatible with the macroscopic fluctuation theory. In fact, if you plug in a current larger than the average here, you would get an L here. The thing that fails is this power. So in fact, this is not compatible with macroscopic fluctuation theory. This behavior, two different scalings, which are certainly related to what Stefano was saying last week. Unfortunately, she's not here today. Where these scalings were observed in the case a long time ago by Derrida and Lebowitz, and then more recently, Popkov should the typical states at a very large current using the beta ansatz, which can be done in the open case as well. And in both cases, the typical states have long-range correlations, which would be in contradiction with the macroscopic fluctuation theory ansatz. So now I will be trying to get something similar for non-integrable versions of the exclusion process. So in that case, I will write the biased Markov matrix as its diagonal part, which doesn't depend on the bias and which is negative and contains the escape rates from every configuration, and the jump part, which is strictly off diagonal and which depends on the bias and contains the jump rate configuration to every other configuration. So the form of those, the entries of that non-diagonal, they contain a current counter, as I said before, which could depend on the site in principle if I wanted to count the currents on every site independently. Then I have a jump rate, which depends on the two configurations that I jump from and to, and also depend explicitly on the site. And then I have an operator which takes a particle in I and tries to put it in I plus 1. These are like spin 1/2 Ising operators. Now I want to choose some, actually I have to choose some physically reasonable jump rates. And so I define them is to take a site-dependent kinetic prefactor, Pi, which I bound from below and above. It can't be too small. I don't want the system to block at one side because the particles cannot. And I also don't want to effectively erase one side by making the particles jump immediately from it. And then an interaction part with a potential V, which is in the sense that potential difference for a jump shouldn't depend too much on the configuration very far from the jump. So it decreases in some way. It doesn't need to be exponentially small. It just needs to decrease. And then the biases that I'll take for the currents are just uniform over all the bonds, because this makes calculations much easier. In that case, that bias matrix has this form, the diagonal part, and then there's a global counting prefactor on the jump part. And now we'll be taking mu to plus or minus infinity, which corresponds to taking the current to plus infinity or to 0. Model being totally asymmetric forbids negative currents, so an infinite negative bias means 0 current in this case. And I will try to estimate the largest eigenvalue of that thing in those two limits. I'll start with the plus infinity limit, the very large current limit, and this is extremely simple. In that case, the part of the biased matrix is the jump part. It has a global prefactor e to the mu over L plus 1, so the largest eigenvalue also has that prefactor. And taking the transform, we find that that L plus 1 here means that the large deviation function will be linear in L. This also contains a constant, which is the largest eigenvalue of M, the jump part, M plus, and I will still need to estimate that constant in case it behaves in some way with respect to L, and I also want to look at the typical states that go with it, so I do need to have a closer look at that matrix, but this is also not very difficult because so in that jump part of the matrix, the potential term just comes out as a matrix similarity, so it doesn't matter. Can also actually remove the site dependence by another matrix similarity, so it also doesn't matter and just gives me a global factor. And I can decide that the product of all the jump rates is 1 without much loss of generality. And what I'm left with is half of an XX spin chain, which is quadratic, exactly, it's free fermions, it's exactly solvable. And by exactly solving it, I get that the largest eigenvalue scales like L over pi, so that the deviation function globally looks like L times some function of j, and also the states corresponding to that largest value look like Coulomb. I have a distribution of a Coulomb gas on an anti-periodic circle of twice the size of the system. It has long-range correlations as 1 over the distance squared. So as you see, this is fairly straightforward and much simpler than using the beta ansatz to solve this, even in the standard case. Now, things get more tricky in the low current limit. In that case, the dominant part of the biased Markov matrix is the escape rates, but that part is constant, so it's not very useful to take a Legendre transform of it. Which means that I need the first correction in mu of that largest eigenvalue. And the way I do that, so now I have an exponential of mu over L plus 1, which is a very small epsilon. So I have to do a perturbation theory around the dominant eigenspace of that diagonal part. And those perturbations will have to be a very high order, because the least number of steps that it takes to get from one configuration to itself is L plus 1. So I will have to do perturbations of order L, at least L plus 1 in that, around that matrix. A nice, very compact way to do that is to use the resolvent. So if you consider any diagonalizable matrix M, and you look at that contour integral of z over z minus m around a contour that contains only a few of the values of m, it's fairly easy to check that what you get when you do that is exactly the part of the spectral decomposition of that matrix with the eigenvalues inside 1. So it's a nice technique for matrix decimation if you want to only keep the slow scale dynamics of a process. And if I apply that to the matrix I have here, I can expand that whole business in epsilon, because everything else is diagonal. There's no issue. I can just expand that expression in epsilon, and then I can project that whole matrix in the dominant eigenspace of MD, which is diagonal, so it's fairly easy to find, and which contains the states that have the lowest escape rate, which means the states that are the most easy to maintain with a low current because they are more stable than the others. So if I do that, what I get is an effective matrix which has entries with a certain prefactor that depends on the number of ways that you can get from one of those slow states to another. And then a power of epsilon, which is the smallest number of steps that you have to make to get from one of those slow states to another one, and then transition between those states. So I'm still interested in the largest eigenvalue of that matrix, which the size of that dominant eigenspace could be very large, I don't know. So the first thing I have to estimate in order to get the largest eigenvalue of this thing is to describe the states which are in that dominant eigenstate, then to analyze the weight of cycles of such states, using that to estimate the minors of this reduced matrix, and then using that the minors and the characteristic polynomial to estimate the largest eigenvalue, or to actually just get a bound on the largest eigenvalue of that matrix. I will not go into the details of how this can be done, but I have a bunch of backup slides if you're interested. I will just show you what those slow states look like. So what I find is that those states have to be completely full to a certain point and completely empty after a certain point, and then there's an area in between where, in principle, anything could happen depending on the potential, the interaction potential that I choose, and the site-dependent rates. I can actually tune the possible configurations in this middle region to be not exactly anything, but at least pretty varied. The important thing is that this region has a certain width, which is smaller than a constant k, which doesn't depend on the size of the system, which means that in the large size limit, this will just be an anti-shock. It will just go from 1 to 0. This bound also means that the number of states that can be of that form is proportional to L. because this thing can be anywhere in the system, but the number of configurations inside is bounded by a constant. And all of this allows me to estimate the first correction around the constant of that largest eigenvalue, which has some exponential behavior with respect to mu with a constant c, and that constant is larger than 2 to the minus k minus 1, which is a constant. That, through a Legendre triangle, means that my large deviation function has a first constant term, which is just the smallest escape rate, and then a dependence on J, which has a prefactor, which is of order at most 0 in L. So it cannot scale with the, it cannot increase with the size of the system. In principle, it could be a negative order in L, but in the cases that I've seen, I think it isn't. Give you a couple of examples of what, so I didn't say that this effective matrix essentially gives us also the effective process in that reduced eigenspace. So here a couple of examples with well-chosen interactions which make a certain class of states be the most stable ones. So for instance, for a width 2 or 4, I have just dynamics between all of those states with the red dot marking one specific site in there, but the actually contains those states translated everywhere in the system. In both of those cases, the large deviation function scale behaves like 1 plus 4 j log j, so that constant is 4. In both of those cases, and in fact in all cases, that process is quasi one-dimensional in configuration space, not in physical space. So it's a much reduced process. Locality is very important, so I told you that I had some paint on the potential, the interaction potential between the parts. And it's, if I add a non-local term, very simple term which just promotes the configuration, the empty configuration and does nothing to the others, everything breaks down. So here I have plots of the logarithm of the largest eigenvalue, well, the first correction of the largest eigenvalue with respect to mu. The curves at the bottom are without that non-local potential, and as you see, they collapse independently of the size of the system very, very quickly in mu. And up there, I just add that potential, and well, the dependence in the size is restored, and I can't say anything. So now that I've described the very, very extreme fluctuations, I don't know how to get any from for the intermediate large deviations analytically, but I can still look at numerics of the spectrum of the biased Markov matrix, which is this. So this is the real part of the spectrum of mu, rescaled in a certain way because everything is exponential in mu for large mu's, so I just divide by something that takes them to a constant. And you can see that for very large mu, this looks like a free fermion spectrum, so you have a density which is a semicircle. For very low mu, the eigenvalues get bunched a lot, and this looks more like a bosonic spectrum with a high degeneracy of every eigenvalue. And so what I've been looking at, describing is the behavior of all the eigenvalues in only the top bunch. And in the middle, you can see a mess, which is where the dynamical phase transition between those two scalings in the size of the system happens. This is for TASEP with nearest neighbor Ising interactions. So it's a simple case. If I took some very complicated potential and actually didn't take something that I would even worse mess, and it's not clear that in general with any potential there's a clear phase transition, but if the potential is well behaved enough, that's what we expect. We can also look at the full complex spectrum at different values of mu just to see a bit clearer what these things look like. And for very large mu, it's pretty clear that this is a free spectrum. For very low mu, there's a very high clustering for every real part of the eigenvalues. And then in the middle, for mu equal to 0, it looks a bit like a spider. So to interpret all of this, well, there's a fairly simple physical explanation for that dynamical phase transition. If you look at some proposed hydrodynamic equation, so coming from the macroscopic fluctuation theory, but putting in a drift which scales with the size of the system, and then rescaling the current by the size to get a small diffusion and still a small noise. Because of the vanishing diffusion, this equation, if you're trying to solve only the deterministic part, this equation will most of the time just be J equals to sigma of rho, because this diffusion, this vanishing viscosity part can only produce localized shocks or boundary layers. So let's plot some sigma of rho. It's very difficult in all generality to get sigma from the microscopics of the system that you're looking at. In fact, in general, it's probably impossible. But there is one thing that I know about sigma because of the exclusion constraint, which is that it is 0 at 0. There's no current for an empty system. There's also no current for a completely full system. So it's also 0 at 1. And if it's well behaved enough, it needs to have a maximum somewhere. That means that J equals sigma has no solution for J above that maximum. So if we now consider a system where the stationary state has a density which is somewhere here at rho 0 with a certain current below the maximum, if I ask the current to fluctuate below the maximal current, it's fairly easy to find that there is a density profile rho which disagrees with deterministic equation only in a localized shock or boundary layer, and which realizes that current. So the system can maintain a current below J max, even if it's a positive fluctuation of the current, can maintain it by localized defect that with a cost that doesn't depend on the size of the system because it's localized. If you want to push the current above J max, however, the system can't do that anymore. You can still look at what the optimal density would be from the macroscopic fluctuation theory rate function, and you would get an answer. You would get a scaling of the large deviation function of the current, which is linear in the. But in fact, the easiest way for the system to realize that larger current is not to only speed up all the particles independently, but also to organize them so that they can jump at the same time altogether, which means to alternate them, which means to introduce correlations in the states of the system, which is what we can do in the limit of very, very large currents. In all cases here, the density goes to 1/2, and long-range correlations appear in the system. So this interpretation was confirmed recently by Beck, Caffery, and Lecomte, who looked at the KMP model where sigma of rho is rho squared, so it's not bounded from above. And in that case, they checked the macroscopic fluctuation theory rate function is in agreement with the exact calculations that were, I don't remember, I think they are exact calculations for any value of the current. Right, so I've been talking about the current, but that resolvent method is actually also applicable to the activity, which is the number of jumps rather than the jumps to the right minus the jumps to the left. Of course, I've been talking about the totally asymmetric exclusion process, which never jumps to the left. So in that case, the activity is the same as the current. But if I look at partially asymmetric simple process with jumps in both directions, and I look at the limit of low activity, and this is in progress, so this is just a teaser. In that case, so I look at the limit of low activity. In that case, the biased Markov matrix still has that constant diagonal part, because I'm only looking at transition quantities, and then has a small epsilon with m plus and m minus in here. In this case, I don't have to do very large order perturbations, because I can use m minus and then m plus to just come back to my state. So I actually only need, maybe only need second order perturbations around MD. It's actually not always the case, because there's two ways to get from one state in MD to itself, in this case. One is to jump forth and back, which has a weight epsilon squared times q, where q is the rate of jumping backwards, and which I take small, at least smaller than 1. And then there is another way, which is just to take one particle and make it run through the whole system, which has a rate of epsilon to the L. But in fact, the probability of that is actually larger, and in the end, you end up comparing epsilon squared to q. And now if we plot the logarithm of the rate function, of the cumulant generating function minus the constant part, we see that there's two different scalings. So I do that for different sizes, different values of the backwards rate q, and different values of the boundary rates. As you see, everything, so the top curves are for some boundary rates fixed to 1, and the bottom curves are for 1/2, so everything depends on the boundary rates, that's fine. But for a given boundary rates, and different sizes and q's, there's a regime of low but not so low activity where nothing depends neither on the size nor on the value of the backwards jumps. That's a regime where particles just go forward because that's the best way to not move. And then for very small activity, the best way to not move is to actually not move and just jump back and forth by one step at a time. And in that case, everything depends on q. Everything depends on the size of the system, and the position of the transition depends on q. And the way that everything depends on the size of the system in this case is inversely so everything is inversely proportional to the size of the system, which would give a large deviation function proportional to the size of the system. So on the other side, for very large activities, everything is exactly the same as large currents, because because that non-diagonal part is still a free fermions chain. Which means that for the activity, you have two dynamical phase transitions. Everything scales with L for positive mu's, and for mu below some threshold, and in the middle, it doesn't depend on L. As far as I know, the two parts which scale with mu were seen before by Lecomte and collaborators, but not that middle part. So in conclusion, if you want more details about everything about the current, you can have a look at this paper, this recent paper. I've told you about, as I said, about the asymptotics of the large deviation of the current. I don't know any analytical way to get at anything in the middle, and especially not to locate the transition and to analyze the transition. So I guess it will have to be done numerically, at least to begin with. The resolvent method that I've used for low current is specific to the totally asymmetric case, because in the partially asymmetric case, the limit of zero current is not for mu going to minus infinity, it's for mu equal to some constant which compensates the bias in the jumps. And in that case, the constant part of the matrix is not diagonal anymore, it is simple exclusion process. And that resolvent method would require to diagonalize that simple exclusion process entirely first in order to do perturbations in it. So the method doesn't apply as easily, but I expect the results to hold for the partially asymmetric case as well, because in the standard ASEP case they do. I also expect the methods and results to extend in some way to different geometries, so for 2 dimensions or on a tree or things like that, and for more varied models, but there is really a lot of things to explore with those methods, and I'm working on it. And then it would be also very interesting to see what happens for models of active matter, whether the drive of equilibrium is internal to the particles rather than a field applied to the whole system, and which should give very different behaviors of pretty much everything. So thank you very much for your attention, and I await your questions. Everything was clear.
Well, so I have to ask a question. So you explained to us approximation of the, let's say, of the top eigenvalue of these matrices mu,
yes.
For large mu and small mu. That was an important part of your computations,
yes.
Analysis. So do you know what kind of error which is made in this approximation?
Yes, so it's for the largest eigenvalue itself, the error that is made is some lower scaling in exponential scaling in mu. So this is just the first term of an expansion in powers of exponential of mu. So the error would be the next power of exponential of mu. Well, actually the preceding power, because it's for negative mu, so the dominant term is the largest power, the smallest power. Sorry. And for the large deviation function, the error is the next term would be j squared, I think, or yes. Yes. So keeping that, there's a subtlety. So the prefactor here in front of the exponential part will be a term linear in j in here. And if you forget that part, the equivalence is, so the equivalence of a function and its Legendre transform with respect to the reference function and its Legendre transform has to be done a bit carefully. You can't forget the j term in the large deviation function, because then you will forget the prefactor in the generating function of cumulants. But as long as you keep the equivalence, is fine.
Okay. So thank you again. Frank has a question.
So why are you hopeful that you can do this in dimension 2?
Because it seems that the results, the methods apply. It's a bit more. So for the high current limit, the fact that the jump part is just proportional to that thing will always be the case if I count the currents in a smart way. But so in two dimensions, there's two currents to be counted. If I only count the current upwards, or so the geometry of the lattice actually seems to matter in that case. But so if I count a current which is not horizontal or vertical, then only the current that I count most will be in the large current limit, because that's the one that's easier to produce. So I will actually just get a collection of independent chains. Then I have to see how those chains interact with each other at the next order, but the scaling of the eigenvalue will be the same. For low current, well, okay, it's a bit more tricky. If I count those two currents, if I allow the particles to only jump in one direction per dimension, I will still have perturbations around the diagonal matrix, which allows me to use the resolvent method fairly easily. So I don't expect the calculation as easy as in this case, but at least to be doable, and I know where to start. Okay. I don't expect the scaling same necessarily. I don't know.
Are there other questions? Okay, so if not, we can thank again all the speakers of this morning.